grant. Okay. Okay, this meeting is being recorded at long last. Okay, Daniele Viganò, stamp scientist at ICE, nice CV, and he's going to speak about his latest work about exoplanet magnetism. So, please.
Thanks. Hi, everyone. We'll try to give an overview of what we have been working in essentially the last couple of years. And I will focus mostly on three works in which most of the team is involved, and especially myself, Albert, but also Shomyo, Tanner, who left, Claudia, and other people. So it's more, let's say, a theoretical study of what we can infer or what we can think about magnetism in exoplanets, in particular in gas giants, because magnetism is one of the things that are least known in the expanding field of exoplanets. So first of all, I will try to give an overview for those of you who are not very familiar with hot Jupiters. What do we mean by hot Jupiters and what do we know about them? So this is a plot, a very recent plot from one of the two most important archival archives of detected exoplanets, in which here you can see the mass and here is the orbital period. So it's essentially the fundamental plane for place the main characteristics of known exoplanets. And we will focus on this region here, in which we have quite massive planets. This is one in unit of Jupiter masses. Actually, this is a minimum mass in some cases, because we have an uncertainty on the viewing angle, but in any case, it's the order of magnitude, let's say, of the size of Jupiter up to the limit with brown dwarfs, which is 13 Jupiter masses, above which you have some burning of deuterium, and then you label those objects brown dwarfs instead of gas giant exoplanets. So in any case, the bulk of these hot Jupiters are in the range of Jupiter mass of a fraction of it, and in some cases, we can have an example of several Jupiter masses. Now, we know many of them. We know several hundreds hot Jupiters nowadays, and this is also because we are observational, we are biased positively towards their detection, because being more massive than rocky planets, we can detect them more easily both in radial velocity and transit. That are the two most important, two most frequent ways in which we detect exoplanets. So for radial velocity, you have two tight companions, star and the planet. Then they orbit around their center of mass. So the more massive is the secondary one, the planet, the more displacement the star will suffer, and so the more signal you can see in the spectrum, in the sense that you can see a modulation of the shift, blue shift or red shift of lines across the orbit of the system. And the other is transit, that is visible if you can see the system edge on. So if basically the planet passes between us and the star, and in that case, just photometrically you can measure a dip, and that is in that case you can also measure the radius. In both cases, the signal that you can detect is much larger if you are dealing with giant planets, and if they are close to their star, which is the case of hot Jupiters, because the orbital period is short, typically few days or less, then it's more likely to happen. So that explains that the abundance of detection of hot Jupiters, but nevertheless, when they were first discovered in the 90s, they came a bit as a surprise, just because in our own solar system, we don't have this kind of object. Gas giants in our system, they are in the outer part of the system, and this diversity has something to do with the formation. It's not the object of this talk, and also it's not my main expertise. But let's say that it's pretty difficult to conceive an in situ formation of hot Jupiter. So the main theory deals with a migration. So the hot Jupiter is formed, the gas giant is formed in the outer part of the system, and then by different mechanisms and also with the interaction of the disk at the beginning, can migrate toward the interior of the disk. And so you can end up having these giants very close to the host star. How common is our type of solar system or this kind of systems is currently not very clear, because there are a lot of observational biases, but it's This explains why it came as a surprise, but now we know that it's pretty normal to have this kind of hot Jupiters tightly orbiting the star. Which are the kind of stars that we can that host hot Jupiters? Here, the different colors mark the different type of stars, from the hotter stars to the more massive stars down to the smallest one. So these are the M dwarfs, and we know relatively few hot Jupiters around M dwarfs, while most of hot Jupiters are detected around F and G stars, so more like solar-like stars. Fundamental characteristic of hot Jupiters come from very basic considerations that if you know the orbital period, then you can infer, knowing the mass of the star, you can infer the separation. And so what one can see is that the radiation coming from the star is pretty high. So a fundamental parameter when we speak about hot Jupiters is the radiation flux from the star, or saying in another way, the equilibrium temperature, which is the temperature at which, basically for a given separation between the star and the planet, is the temperature at which the upper atmosphere will be at equilibrium, assuming a certain number of things like zero albedo and so on, but it gives you an order of magnitude. So just to give you an idea, the equilibrium temperature for our cold Jupiter is few hundred Kelvin, while for hot Jupiters, typically we deal with between 1,000 and 2,000, with some cases approaching 3,000 or even more Kelvin. That means that their atmosphere is very hot. And another thing to notice is that these planets are supposedly supposed to be tidally low. Why? Because the tidal forces that will slow down their rotation are very intense, and the closer they are to the host star, the fastest will be the time scale over which this tidal locking will happen. And that means that we can define a day side and a night side exactly like the moon or the Earth. The moon, we always see a face that is towards us, and the night and the dark side of the moon, that is the opposite side. So the same way happens with hot Jupiters around hot Jupiters, or even rocky planets that orbit very close to their stars. So we can define a day side, a night side, separated by what we call a terminator, that will be, say, corresponding to the sunset. And the fact that we have a day side and night side means that the radiation is making the day side very hotter than the night side. This implies that you have a strong gradient of temperature from one side to the other of the planet, and that will induce thermal winds, which are very fast. They can be as fast as the speed of sound in the locally, and they basically they circulate in the uppermost layers of the star, of the planet, let's say below 10 bar or less, or bar or tens of bars at most. Here, these are just theoretical pictures of what should happen. It's a very basic consideration. So the most of the circulation will happen following this red line. So you will have zonal jets that try to distribute azimutally, so to bring the excess of heat from the day side to the night side. But you can also have meridional circulations and other kinds of circulation which are more complicated. And everything will depend also on the magnetic fields, as we shall see. Now, these are not only theoretical ideas, because they can actually be somehow you can measure a bit, or you can infer from the reflected light of the exoplanets. You can infer somehow the surface temperature of these objects, and typically what you can see is that to the substellar point, which is the point at the surface of the planet to which the star is at zenith, so that takes perpendicularly the radiation, it's hotter than the rest. Although there is usually a shift of a few degrees to the east side, and in a few cases to the west side. So somehow, for some reason that has to do with the circulation, the hottest point is not exactly the one at which the radiation is exactly perpendicular, but it's a bit shifted. And that is telling us that there is some advection, so some wind that is somehow shifting the hottest part of the surface, usually to the east, but it sometimes can be also to the west, just because the circulation is complex, and you can have layers where where you have an east jet, and others you have west jet. These relies on theoretical models, but observation. We also see this kind of diversity in a few cases in which you can infer this kind of theories. Another very important characteristic is that most hot Jupiters show an inflated radius. What does it mean? Well, basically, we can measure for those systems which are transiting, so we can measure the radius beside the mass. What we can see is that as the hotter they are, the more inflated the radius is. Most of these objects are more or less the same age of Jupiter. Nevertheless, some of them can have and similar masses, but they can have up to twice the size of Jupiter. So they're very puffy, they are very inflated. And this has been noticed since the very beginning. The first systems were already noticed to have 20%, 30% higher radius, and nowadays we have systems that can be twice the size of Jupiter. Now, observationally, what one can see is that this inflation doesn't correlate much with the orbital period, but correlates a lot with the equilibrium temperature or the irradiation. So there is a clear trend with the amount of radiation received from the star. And there is also a kind of trend with the mass, in the sense that low mass exoplanets are more inflated than the high mass. The second thing, this trend with mass is somehow intuitive, because if a planet is more massive, it's more compact, so its own gravity is more. So whatever is the mechanisms is trying to lift the planet more puffy will be counteracted by gravity easily. So it's more difficult to inflate a very massive planet, regardless of what is the mechanism that generates this inflation. However, the equilibrium temperature trend, so the fact that the hotter is the planet, the more inflated it is, this tells us a lot about their underlying mechanism. So what are the possible explanation? Well, one has to start thinking about cooling models. So this is a starting point, because one needs to know how a gas giant evolves in time. And in order to do that, you just use basically a stellar evolution equation, simplified because you take out basically the nuclear fusion, but for the rest, you can use stellar codes. In our case, you use MESA, any stellar code taking out basically any stellar mechanism, in particular the nuclear fusion principle can work. And basically you evolve the sequence of hydrostatic equilibrium, considering the long-term cooling, the fact that the planet is radiating away the energy, so the internal entropy and the temperature is slowly decreasing. And at every time step, you calculate the internal structure at equilibrium. So with simply the hydrostatic equilibrium, so basically the mass continuity and the equilibrium between pressure gradient and gravity. You consider also the local gradient of temperature, which is said to be the smallest between the radiative and convective. So you can identify at any given time what is the size of the convective. This is standard stellar evolution, explained in a few seconds in a naive way, but it's what you basically need to know in order to do prediction for planets as well. Now, in general, for Jupiter or for normal gas giants that have no extra heat involved, you expect that in time, the internal entropy decreases, so the planet cools down and shrinks. So slowly, maybe Jupiter was born with a few carbon Jupiter radii, and in time, it slowly cools down and shrinks. Now, with hot Jupiters, you have to introduce another effect, which is the radiation. Why is that important? Well, because if you are radiating a lot the outer atmosphere, you can have a blanketing effect. It's like putting a blanket on top of something that is trying to cool down. The effect is to delay such a cooling, right? You can imagine even a saucepan with hot water, if you put a lid on top, it will cool down slower, right? So having this continuous stellar irradiation that is keeping the outer part of the planet essentially, at the day side at least, essentially at the same temperature, will slow down the. And that works, but can explain more or less 20, maybe 30% of increase of radius at giga-year, which is good. So in this plot in particular, we are doing some simple tests that many other people did, of course, they had to know. in which you take a case with no irradiation, which is the black curve here. In solid is 1 Jupiter mass, and with dash dot is 8 Jupiter masses. And what you can see is that when you consider an irradiation corresponding to 15 or 2000 Kelvin, so pretty standard range for Jupiters, then you can see that you can inflate a bit and have maybe 1.1, 1.2, 1.3 Jupiter radius, but not more than that. Remember, I said before that we have objects that are here around 1.6, and we have a few with 1.8 or approaching 2 Jupiter radius. So how to explain that? Well, another thing to consider is that, yeah, as I said before, we know at each time step, we know the internal structure, and in general, what you expect for gas giant is that most of the interior is convective, unless until the very outermost layers. And this radiative region, which is in the outer part, is larger for hot Jupiters because you have an irradiation that keeps the temperature more homogeneous, more, let's say, decreases the gradient of temperature that you have in the outermost part, and so you suppress the convection in these layers. But we are speaking about below maybe 100 bars. When you consider that, you can also identify how is the internal structure, how it evolves in time, and these are the PT diagrams in which you show at a given time this at every pressure what is the local temperature. So you can go up to the innermost part of the planet, which are here, 10 to the 7 bar, and see what is the temperature. So the temperature typically passes from 1000 Kelvin in the outer part set by the radiation up to a few 10 to the 4 Kelvin, and it cools down. So at the beginning is here, and then darker shades in later ages. Okay, so you can follow also how it evolves with the internal structure, and this is very important if you want to infer things like internal magnetic fields, as we will see later. And here you see the role of the separation to the star. So the more separated it is, which is the values down here, the more this PT profile becomes diagonal, in the sense that the convective part here, so the diagonal means that it's an adiabatic relation. So basically you have a power law between pressure and temperatures down to very low pressure of 1 bar. But when you consider small separation, then you have the irradiation, and basically you have a bigger part of the star which is more almost isothermal. So then the relation becomes more vertical in this PT diagram, and that is because the outermost layer are kept very hot, so that the gradient of temperature here is lower, and so in this case you don't have convection. Okay. Now, say that are the basic ingredients to understand all the rest. What are the theories to explain the radius inflation, which is the main object of our study? Well, in the beginning, people were proposing that you can have delayed cooling due to the enhanced opacities. So for some reason, chemical composition or processes that happens for hot Jupiters could explain that. And that can work actually in some cases, but stretching the models, you can add up to 1.4 Jupiter. You cannot reach more than that. So maybe they contribute something, can be the case for some planets or for all of them, we don't know. But it cannot be the driving effect. Also because it would not be clear what is the trend, the observed trend with the radiation flux. It's not clear how it would enter to explain this. Other things are reduced heat transfer due to double diffusive convection. So you suppress partially the mechanical convection, you're left only with chemical convection inside, and that will basically make the transport of internal heat to the exterior less efficient, causing a delay in cooling. But again, these were proposed when the number of hot Jupiters with inflated radius were not too many. And nowadays we know that what you really need in order to explain especially the most extreme inflation scene is that you need to add some heat inside the planet, especially in the convective part of the planet. So there are several studies, and one of the most famous is by Kovacic and Yudin in 2017, another paper. All of them show that when you introduce an additional heat source in the energy equation, then you can explain this radius, basically because you maintain the internal entropy higher. So instead of shrinking, the planet at some point stalls the cooling and shrinking, and stays much more inflated than in the absence of it. So by doing that, playing with parameters, you can reach up to 1.5, 1.6, 1.8 Jupiter radial. Okay. And a very important thing is that such a mechanism is effective if you put the heat in the convective region. To understand this very intuitively is that if you put in the convective, if you put some heat source in any given location within the convective region, the convection, since it's a fast mechanism compared to the cooling timescale, it will redistribute this excess of heat in the rest of the interior of the planet. And that will be effective because it will heat up the entire planet and will cause this extra inflation. Now, these works were not specifying what is the physical mechanism that can give you such an extra heat. So what is that? There were several theories. There still are several theories. And here I list I think the three main ones. One is tidal effect. So you can have tidal dissipation because of eccentricity. And that can actually give you, if the parameter can give you enough dissipation, but then at some point the eccentricity will tend to be very low because the orbits will become synchronized. So that mechanism can work at very early stages, but not at gigayear problem, unless you find a mechanism to keep the eccentricity high. So there are some works on that, but again, these were the early couple of decades ago. They were more trendy. Another possibility is to have turbulence that is dragged inside. So if you have turbulence, you can dissipate part of the small-scale turbulence into heat. And if you're able to drag this turbulence in the wind region when you have this thermal wind, then you could, in principle, deposit the heat inside in the conductive region. These models might work. The problem is that there are no really quantitative studies. We have worked in this direction with Claudia, and we show through the electromagnetic field, and apparently this turbulence is pretty difficult to be triggered. So doesn't seem very promising. So overall, I think the community agrees, or most of the people involved in this study agrees, that the ohmic dissipation is the ohmic dissipation models on which I will focus on the rest of the talk is the most relevant, is the most promising one. Not sure if it's always the dominant one, but at least there are also many quantitative studies with which we can play. And in order to do that, we need to model the magnetic fields in the planet. What do we know of magnetism in exoplanets? Basically nothing. The only reference we constantly have is Jupiter, for which we have a very good measurement, and it's the most magnetized object in the solar system. But besides that, there are just an indirect inference of values, which are really, for instance, there are radio emission, that coherent radio emission can track the value of magnetic field, but when people follow up this observation, we didn't find the same signal. So there is no real measurement of magnetic field for this. There are some other that are related with modulation of chromospheric activity, modulation with the orbit of the planet, and one can, via modeling such interaction between stars and planets, can infer the value of the magnetic field on the planet, but I think it's really, really model dependent. So we have really no clue of how much is the magnetic field from an observational point of view. So from a theoretical point of view, what we can see? Well, let's start from the very basics, just for maybe some of you are not very familiar with MHD or magnetic field. So very general, generally speaking, what you need to sustain a magnetic field is an electrically conducting fluid. So you need a quite high conductivity. And you need that these carriers of the charge need to have some bulk motion. It can be rotation, differential rotation, convection, shear, turbulence, but this material needs to move. Then the timescale and intensity of the magnetic field will depend on many things. MHD, magnetic hydrodynamics, is a very complex topic and very problem dependent, but in general, the timescales of survival or amplification or decay of magnetic field depend basically on the ratio between the effectiveness of these movements here and the resistivity of the material. Okay, so in astrophysics, this is why you can have a huge range of different values when you go from interstellar medium down to compact objects. The values of magnetic field change basically by 20 orders of magnitude in total, because also you have then other effects like flux conservation when you compress an object and you collapse it. But in any case, let's say that the underlying mechanism, although the scales and the intensity are different, the underlying mechanism of energy are universal. And in different astronomical objects, also the fluid responsible for the generation of field is different. And we shall see that for gas giant, what is relevant is a phase which is called metallic hydrogen in the interior of the planet, while in the exterior are ionized alkali metals. Now, what is this metallic hydrogen I just mentioned? Well, when you take hydrogen and you compress it a lot, then at some point it becomes basically, it behaves like a metal. Okay. So basically the atoms of hydrogen are so packed that the electrons are not tied to each ion, to each proton anymore. So the electrons are pretty free to move. And in that region, in this regime, just like in a metal, the conductivity increases a lot. By the way, this I find it funny because in astrophysics, we call metals whatever is not hydrogen and helium, but then it turns out that hydrogen many times can be in a metallic state. So it's a kind of taxonomic conflict with the rest of physics, for which in physics metal is a certain kind of element, not whatever is not light. No? Anyway, besides this, it's important because this metallic hydrogen state is present probably in gas giant and also in brown dwarfs, so it's pretty abundant in the universe. It's a state that is not so exotic. And actually, it has been found also in laboratory very recently. An experiment that found it with some setup. Of course, it's not exactly the same condition, but they found what was predicted by basically molecular dynamics and density functional theory, that are the ones that in simulation you can predict the transport properties of this state. So what you can see here is that the conductivity in this region, this is the interior of Jupiter, is much higher than in the exterior. So when you have such a high value of conductivity, you can sustain current and you can generate a magnetic field. And this is the so-called dynamo region. Okay. Now, the conductivity we use in our study comes from a paper of last year that they put together. They raised the most recent calculation, and bottom line, there are not so many points in the density temperature space of parameter. So one needs to interpolate, but let's say that at very high densities, which would be more or less the inner part of gas giant, the conductivity depends mostly and not very steeply on the density and not much on the temperature, while in the outer layer, the temperature is relevant, because basically the ionization that you get in the inside is due to the pressure and in the outside is due to the temperature. Now, armed with that, one can model the magnetic field for gas giants. There have been several attempts in the last decade to model the details of Jovian magnetic field. Also, so there are some similarities somehow. One cannot hope to reproduce exactly the observed configuration of Jupiter, but at least there are some features. The scale of the magnetic spot that you get can be similar. So there have been a lot of advances in the last 10 years or so. Albert also worked in this direction. It's a paper that has just been published. He modeled basically the values of the magnetic field with the dynamo code at different time of a cold Jupiter, and found some decay in time, meaning that if you take the conditions, the thermodynamic condition at early ages, the magnetic field that you get from dynamo simulation is higher than with the condition that you get at later stages, basically because you have less temperature gradient later on, and that would mean that the convection is somehow slower, or say it better, that the dynamo is less efficient. Now, there are, of course, many studies of dynamo simulations in the last decade. And there are some important things that one can notice, that one can do a scaling law, comparing with the observations, taking a Jupiter, Earth, and low mass stars. There are some famous relations that basically relate the amount of magnetic field with the internal convective flux. So the more convective flux you have, the more heat you can transport by convection, the larger will be the magnetic field. And these kind of predictions are supported by these observational trends that are seen across a pretty wide range from basically the Earth to low mass, fully convective stars. That is for the interior part. What happens in the exterior? In the exterior, as I said before, what you have is thermal ionization of alkali metals because the outermost layer are so hot. I remind you that you have irradiation, so you have 1,500 degrees or 2,000. Then under those conditions, you have potassium, sodium, calcium that start becoming ionized. So you have ionization, you have basically the outermost layer, although these elements are not very abundant, but they are there and they can carry some current. And these currents, if they are intense enough, can generate their own magnetic field, starting from the magnetic field that you have at the base. And in order to understand this, just a simple sketch of how MHD works and how, in particular, for this problem, how one can describe the induced field in the atmosphere. In MHD, there are two main effects. One is the advection, so the fact that you have basically in ideal MHD, you have your fluid is moving and you have a magnetic field. The magnetic field lines will move together with the fluid. This is called Rosenin flux theorem, in which if you take a plasma flow, you can see how the line moves at a later time. Okay. While the resistivity, what it tends to do is to simplify the configuration of the magnetic field, to straighten the line, to reduce basically the electric current. The more complex is the line, the more current you need to support it. And the resistivity, what it does by collision, microscopic collision of the particles that are carrying the current, are trying to basically diminish this current and so simplify the magnetic field lines. Now, in our scenario, what you have is that if you have a magnetic field like this coming from the interior, you have some winds which have some kind of differential rotation because they are more intense in one region than the other. So when you are imagine that you have a wind that is acting on here, what it does, if this is a magnetic field lines, you do like this. Now, this is not elastic. This thing comes better when you have an elastic rope. But in a way, what you have is that you bend the magnetic field lines and you stretch it. And by stretching it, two things happen. One, that the magnetic field lines become twisted in the azimuthal direction, in the direction of the wind. And the other is that you amplify the magnetic field because you stretch these lines, and the more stretch out the line, the more intense is the magnetic. So this is called the winding mechanism. It's well known. It's also basically it has to do with the omega effect, with shears. So they are just different names of what I tried to explain in detail. Now, in our case, you have then a seed magnetic field that comes from the interior, and you can wind it up and amplify. When you have that, there are two effects to consider. One is the effect on the circulation of the wind itself. You have a feedback on it because the magnetic field can become intense enough to slow down the wind by Lorentz force. So you kind of have it's called a magnetic drag. So you take the equation and you see how you can write this Lorentz force considering this wind. Then what you have is that the presence of the magnetic field that comes from inside means that it's more difficult for the wind to circulate. The more intense is the field, the slower will be the magnetic field. So in principle, the higher the magnetic field, the larger you can maintain differences of temperature because the wind is trying to get rid of the difference of temperature between day side and night side. But if you have a strong magnetic field, there will be more temperature difference from one side to the other. So there are several studies aimed just to reproduce these circulation modes. In our case, we want to instead see how is the dissipation inside, because although the wind is here, let's see, this is 1 bar, the typical depth at which the wind circulates, you see that the disturbance of the field propagates also in the other region because the field is connected. So even though you do things only here, you have a wind only here, you will have a generation of field also deep down. And this, how deep down, depends on the conductivity. So mathematically, you can formalize this, you can impose a continuity equation on the current. It's not the point to describe all the formalism. This has been done in the past, but what we did in this study is to introduce this Ohmic heat as an additional source heat in the evolution code, basically prescribing what are the current profile and the conductivity profile. This code is 1D. I didn't say it before, but it's 1D because basically you care only about the radial the radial gradient. And so it's not up to study, for instance, what happens exactly in the atmosphere. So the atmosphere is kind of very simplified, but we care about the interior in this study. So that's fine, is what also people have been doing in this field. And usually people parameterize the extra heat you put as efficiency, as ohmic efficiency, which is the ratio between the ohmic heating and the radiation luminosity. So the amount of heat you receive from the star over the entire surface of the planet. Typically, people need order of up to a few percent to inflate the planet enough. And actually, if you put more than that, the planet blows up because it's too heated. So we did this, and this is what Alberti is about to submit. So we work in two directions. One is to look at the structure inside the planet. In particular, Alberti is focusing on trying to quantify the Rossby number, that is basically a ratio between the timescale of rotation versus the timescale of convection. The lower is the Rossby number, the more important is the rotation. So we are in the fast rotating regime where the scaling laws of magnetic field that I explained above are supposed to follow. And Alberti is showing in his paper that is about to submit that basically for any combination of separation, stellar mass, stellar planet, at most of the depth inside the planet, the Rossby number is small. So hot Jupiters, although they are tidally locked, so their rotation, which is equal to the orbital period, is a few days, is still considered a fast rotation. Fast rotation in terms of this Rossby number. Then the other thing is that depending on where you put the heat, put it in the center or more in the outermost layer, different things can happen at the level of where is the convection. In particular, if you put the heat mostly inside the planet, you can maintain a big chunk of region, basically maintain the original convection size. So you have an almost fully convective planet. But if most of the heat is deposited in the outer part of the convective region, then you break this convection, basically because you put a lot of heat inside the outermost layers, which are in principle colder. And so instead of having a diagonal like this, you smooth out or even invert the gradient of temperature so that in these regions here, you don't have convection anymore. You are in the radiated region. So when you consider this, one can see that if you consider heat put mostly inside the planet, you maintain the convection, otherwise you can break it. And the thing is that this case in which most of the heat is deposited in the outermost layers is the realistic one, because this I will show you in a while. But basically, when you consider the realistic profiles of current and conductivity, most of the heat is deposited inside. So you expect that you can break convection. This is something new that we discovered with this study. With that, Albert can also infer what is the amount of dynamo field, so the field produced inside, using these scaling laws. And what you can see again is that if you put a lot of heat inside the star, you get magnetic field which can be very, very high, up to many hundreds of those. But if you consider a more realistic distribution of heat and you apply the scaling law, considering that in a large part the convective flux is very low, then the magnetic field is pretty low. It's basically the order of Jupiter. And that is something that has not been considered so far in the literature, because the literature usually people assume this scenario, in which the hotter is the planet, the more magnetic field induced, so the more also the dynamo will be strong. And probably it's not the case. And Albert also is providing some estimate for the power available for detectable signature of star-planet interaction and radio emission. And what you can see again is that basically when you consider a realistic profile like this, you have very little hope of radio emission, of radio detection, because it's weak, and also because in most cases it's below the atmospheric cutoff of 10 megahertz, which is below which we cannot see anything from the ground because we have the atmosphere that's not already. Now, to conclude, going back to the radius inflation, we implemented the latest values of conductivities. Basically, these are just different cases in which this is a typical profile. You can see that up to 10 to the 3 bar is pretty flat or doesn't vary so much, but then it increases a lot because here is where the matter becomes the state of metallic hydrogen. So considering this and considering the currents that are induced, this is the kind of profile for the internal heat that you have. Is that you see, it's a kind of steep decay towards the interior, so most of the heat produced is deposited in the outer side. So you can expect to have this suppression of convection. And using this model, so playing basically with the normalization that we forced to have by first principle to be proportional to the velocity of the wind and to the background field that we can evolve with the scaling laws, we can see how much is the current, how much is the deposit heat, and how much is the radius evolving. And here I'm summarizing, we had many models, but basically for different equilibrium temperature, you can see that the radius can become more and more large, becomes larger and larger. We can infer, grosso modo, the values of the average wind velocities, and what we can see is that for temperature of this order, we get kilometer per second, which is in line with what people expect from global circulation models. But then this velocity drops down a lot if you consider larger temperature or high masses. And this is because with high temperature or high masses, you have larger magnetic fields, so you have more magnetic drag on the winds. So you do expect that the winds will be much lower, up to tens of meters instead of kilometers per second. This is a bit in line with what people dealing with climate models find. And a peculiar thing that we found, it's a novel thing that we find in our model, is that the ohmic efficiency, so the ratio between the total deposit heat and the irradiated luminosity, is not constant in time, which was a basic assumption taken by virtually all the previous studies. We find that it's not the case. The ohmic efficiency can drop by 1 or 2 orders of magnitude, and this modifies a lot the way the radius evolves. Particularly, the other study were finding that the radius at some point stalls, so you have a plateau. In our case, we find something different. The shrinking continues, although you basically slow down the shrinking. And one main thing, this is complementary to what I showed before in the study of Albert, is that what we find is that when you consider the magnetic field that you can have, is probably in most cases of the order of Jupiter, few GOES. It's very difficult to have hundreds of GOES like people claim for hot Jupiters, unless you have massive hot Jupiters for which somehow they are less sensitive to whatever happened in the atmosphere, so it's difficult to break the convection. What you see here for the magnetic fields, and with this I conclude, are actually the effect of suppressing the convection, and is an effect of a feedback that we propose in the paper that we just submitted. That is, I showed you before that the total amount of currents that you expect is proportional to the magnetic field. Now, if you have a lot of heat, you suppress the convection. If you suppress the convection, the magnetic field that you will have from the inside is less. So also the induced field will be less. So the ohmic heating will be less. And the ohmic heating will be less, so you can restore the convection. When you restore the convection, the magnetic field is larger, the dissipation is larger, the heat is larger, and you suppress again the convection, and you can do this in a loop. In our study, we are not able to assess the time scales, because probably you need to do it with a different code that takes care of different time scales. But it's a very interesting mechanism that has not been considered so far, as far as I know. And with this, I conclude with the main point that I already made. So thanks for your attention.
Time for questions.
First, well, thank you for this very nice talk. And I have 2 little questions. One, if there is some portion of solid or metallic helium inside.
Okay, there is what is called helium rain that's been proposed especially for Saturn, and so planets which are less massive than Jupiter, because under those pressure, helium and hydrogen are not miscible, so you cannot mix them. So that basically you have that the helium is not mixed, and you have this kind of, they call it helium rain, in the sense that the rain will start to precipitate to lower values. And this has implication, this is a strong implication actually, because in that situation, then probably you have a layer will behave differently also from a conductivity point of view, and can affect the magnetic field. It could explain why Saturn is also less magnetic than Jupiter.
Thank you. Well, the second question is about exo-Jupiters. So you said, of course, hot Jupiters are easier to find, and there are several hundreds. And so, how many Jupiters have been found?
We have. I don't know the number. I think that they are less than Jupiters. But let me go to the very first slide. Maybe I went a bit fast on the first slide, but yeah. So this is the orbital period, and this is the mass. No? So let's say that these are Jupiter. This is one. So in the mass of Jupiter, you see that you have a lot of cold Jupiters as well. Cold in the sense that their orbital period is comparable to Jupiter, or anyway, that their radiation is not relevant.
And from this, we infer that our solar system is in some way special or not, or statistically within.
I'm not an expert on formation and let's say mechanics of systems. I don't know what I think, but it's little to do. But that probably Jupiter, our cold Jupiter, the outer part, has played quite a big role as a shield to clean up a bit all the debris. Maybe Joseph Maria will know more about this.
That seems to be very important.
Yeah, so I don't know in those systems if I guess if you don't have a gas giant in the outer part, you will be exposed for a much longer time to impacts that can cause extinction, maybe cause to have less complex life. I don't know, but it's just a guess. I don't know how much one can quantify this, but is how complex it is, I don't know. Maybe Juan Carlos will know more about what you can infer.
Thanks for the nice talk. I'm also curious about this metallic. You know, is this something that can be proven in the lab?
They recently got it in a Nature paper of 2 or 3 years ago, in which they reproduced it. So this is in planet is supposed to appear around 1 megabar or fraction of megabar, and they reproduced it very recently because
Temperatures up to?
Temperatures are some thousands of Kelvin. Yeah, for when the planet is old, so it's pretty cold. Yeah, it's maybe 5,000 Kelvin. So I don't know in laboratory if they reproduce those conditions, or I don't know which part of the diagram they're in, because this where is it? No, it's not there. In the here is a bit the phase diagram for hydrogen, and of course there are also uncertainties. These are different studies, but there is a region which is metallic, a region which is fluid but not metallic, and then the region in which is solid. So yeah, we know this part here. So I'm not sure in the laboratory where they place them. I guess not exactly the same point as in Jupiter for the temperature, I guess. But I'm not sure.
Quick last question. Everybody's coming for pizza, so if you can hold it here and thank Daniele again.